Hello and welcome to One Promise of 5G, Everyday Millimeter Waves, What This Means for Standards and Measurements with Mr. Roger Nichols. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by Keysight Technologies and MTTS. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archive webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume, and you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Mr. Roger Nichols has been directing Keysight's 5G programs for over 4 years now. His 33 years of engineering and management experience in wireless test and measurement at Hewlett-Packard, Agilent Technologies, and Keysight spans roles in manufacturing, R&D, and marketing. He has worked in programs starting with analog cellular radio, evolving to 5G, and on every standard in between. He spent 7 years as the Senior Marketing Director for Keysight's or Agilent's mobile broadband division, responsible for the wireless test sets and systems used in all major design and certification labs, as well as manufacturing facilities worldwide. Now it's my pleasure to turn the virtual podium over to Mr. Roger Nichols for One Promise of 5G, Everyday Millimeter Waves, What This Means for Standards and Measurements. Roger?
Thanks, Mike, and welcome everybody. Thank you so much for attending. It's a pleasure for me to be virtually anyway in front of everybody, and certainly I look forward to the conversation today, being able to tell you a little bit about what's going on in 5G, especially in the millimeter wave space, and also in the to get your questions. So let's make sure that my sound is okay.
Yeah, you broke up for just a second there, but I think you're okay now.
All right. So keep me honest. Thank you.
I will.
We're going to start with a little discussion about hype. The commercial communications industry is full of this, and even though this particular topic is not specific to millimeter wave, you'll see hype across the industry in millimeter wave and everything having to do with 5G. About a year ago, I found this particular article, and the suggestion here is that we will have 1 trillion IoT devices connected in a quick 20 years. So a couple of issues with this. First of all, last time I checked, 20 years did not go by that quickly. It seemed like it when the kids are small. But 1 trillion devices, 1 trillion is a big number. And let's take a look and see, just as an exploration of the possibility of hype, what does that really mean? Most of the people on this webcast are engineers, I assume, and I believe we all understand logarithms and orders of magnitude. So what does it take to get 1 trillion devices connected in 20 years? So if you do the math, it works out to the need to manufacture these at a rate of about 1,600 per second. And during the course of the next 20 years, you can't have any of them fail, and you can't have any of them fall out or get retired without being replaced. So just at a rate of 1,600 per second, you'll get to 1 trillion devices that are at least manufactured and potentially, hopefully, connected in 20 years. Now, for reference, the number of mobile phones that are manufactured in the world today is about 100 per second. So getting up to 1,600 is a lot of work, and clearly IoT devices are not going to be mobile phones. They're going to be much simpler. In some cases, very, very easy to manufacture and connect. I saw a great presentation a few months ago about a person who developed the first FDA-approved connected pill that you would swallow. To get to 1 trillion devices, you'd have to give 140 pills a day to everybody in the world. And so I'm not convinced we're going to get to 1 trillion, but let's say we really can make them that fast, and there will be uses for 1 trillion devices that are connected within 20 years. Well, let's look at another perspective on this. Let's say these are all connected, and they're all connected over the air, some way or another. If you look at the signaling demand only, not the payload, not the information that actually gets exchanged, but just the signaling that maintains the link. And let's assume that we average 10 bits per second of signaling per device. Now, some would say, now, Roger, 10 bits per second is a pretty high number because these IoT devices may consume a lot less data than that, and hence the signaling would be even lower. And I would suggest that maybe that's true, but some of these IoT devices will be very high data demand, very low latency demand, like in the automotive and transportation industry. So I just picked an arbitrary 10 bits per second. That means that just for signaling, the world would generate and consume 3 exabytes of signaling data per month. Now, for reference, the second quarter of 2018, the world consumed about 16 exabytes per month in total mobile data. Now, that is growing very fast, and so maybe 3 exabytes isn't that much, but really, I think 1 trillion is kind of a big number, and my concern is that there's a lot of hype that will cause a number of people to be misled, and so I would suggest that perhaps 1 trillion devices in 20 years is bull. Now, we're going to move on to millimeter wave, where you're also going to see a lot of hype. I won't go into a lot of details there, but I will describe some of the challenges that we have to address. One of those is the concept of random access. And mobile systems all have a channel that is devoted to random access. And one might say, well, what is this physical channel, physical random access channel, the PRACH? Why is that important? And that's because people operating in the cellular environment are random. We behave in random ways. You cannot really predict these. The psychologists might be able to predict it, but in a one-off situation, it is quite difficult. And examples include people coming into new cells or new cities. You know, when you land on an airplane, you see everybody turn on their device to check their email or their Facebook and upload their videos. And this all happens at random times. We don't all turn them on at the same time, even though it seems that way when that airplane lands. But then people are moving around in crowded areas and behaving in ways that are not necessarily predictable, moving in and out of cells, whether they're small cells or large cells. And this behavior is quite random, and it varies over the course of the day, like in a busy train station. And then there's certain behaviors that tend to be somewhat random, using social media, when you're uploading videos, downloading videos, that kind of thing. And every one of those initiates communication between the device and the network that starts out as something that would happen random. You push that button on your device, the system has to be able to respond. So what is this physical random access channel? Well, it's the first time that a mobile device and a network are going to interact with each other. So when you select the cell that you're going to behave in and reselect the cell, initial access when you first turn on your device, camping on the cell, and even the call setup and handover, because anyone can initiate a call to you at a random time, and handovers happen depending on physical motion, which is also not necessarily predictable. And of course, it requires the right frequency, the right power level to minimize interference issues, and the right timing advance of your signaling, which is meant to also minimize interference based on your respective distance from the cell site and also your relative velocity with respect to the cell site. So the timing advance of the signaling is going to change. Now, in what we call FR1, or the sub-6 gigahertz frequencies, this really didn't have a spatial element. The interface, in this case, we're just looking at a top view schematic of a 3-sectored cell in a typical mobile environment. And let's look at sector A. The physical random access channel exists throughout that sector. And regardless of where the device was in that sector, you could hear the channel. The device would be able to interact with the base station and get synchronized and set the call up without any problem. But when you get to a point of a directional signal, and with these, what we're going to call millimeter wave signals, which we want everybody to use on an everyday basis, we have to put high gain antennas at both the base station and the mobile device. And I had a little fun with this picture by masking taping a fixed gain horn antenna to my iPhone to demonstrate some things to some people. But you can imagine that if I'm going to initiate a call with a base station, I can make sure that antenna is pointed in the right direction. But if I'm not pointed in the right direction, there may be no link at all. And this is new to the millimeter wave space. So having the right direction and that physical random access channel is going to be very important. And it adds a very complex set of dimensions to making this work. Now, how do you overcome this? Because it's not just random access, it is the search and acquisition of the signal, the tracking of the signal as you move around, refining the beam as you move and deal with obstacles and interference, and also switching the beams depending on moving in and out of cells and service areas, and recognizing when to fall back to maybe a lower frequency to maintain a link. All those kinds of things have to be considered. Well, here's one way to approach this, and I usually do this talk in front of a live audience, and I ask everybody if you know what this device is in the photograph in the picture. And the best answer I got so far is somebody said that looked like the Death Star. Well, it is not the Death Star. That is a picture of Telstar, the very first communications satellite that was launched about 12 days before I was born in 1962. And this was a transponder of television and telegraph signals, and kind of an experiment more than anything, because it really only served for a few months, and this is because this is in the days when we were still learning about how harsh the radiation environment was once you got outside the Earth's atmosphere. Now, this device was not a geosynchronous orbit. You can see the apogee and perigee down there in the lower right, and it did rotate for the sake of stability at about 200 revolutions per minute. So what did they do with this traveling wave tube downlink power at about 4.5 watts? And they had to put some antennas on there to provide a little bit of gain. And so from the standpoint of the receive and the uplink and, of course, the transmit on the downlink, they had 72 and 48 antennas respectively. And as this thing was spinning, one or two of those antennas at least was pointing to where it needed to be to the Earth gateway to which it was communicating. Now, this is one way to overcome the directional issue, but I don't think that most of us are going to stand and spin around constantly to make sure that our devices are connected. And nor are we going to carry devices that have rotating antennas, at least not antennas that physically rotate. And so really there's other ways we're going to have to deal with this. The millimeter wave signals have a higher loss through the just the basic laws of physics. And what we're going to have to do is have steerable antennas and then a complex protocol stack that ensures that those antennas are steered in the right direction to maintain a link and make sure that we're all very happy with the service that we're going to get. So I'll get into a little bit about what's going on for standards and measurement and ask that you lend me your ear, at least for the rest of the hour. I'll go through a little bit of a primer about what happens in the standards environment and the status of what's going on for millimeter wave, and then just a few examples of the measurement challenges. So first, an introduction to 3GPP. This is called the Third Generation Partnership Program. Interestingly enough, they're working on the 5th generation now. And the overview of the latest release of the spec is 89 pages, and this is a photograph of the actual overview. You can look that up. It's TR 21.915, and the actual spec is significantly more than this. These are fairly complex standards because they have to be, devices have to work the same everywhere. And the environment that 3GPP operates in is part of a bigger ecosystem. There is a regulatory foundation at the base, which is typically a national or regional basis, things like the FCC in the US or MIC in Japan or Ofcom in the UK. And the standards kind of sits on top of that. The standards have to operate within a regulatory environment. You could say regulations are also standards, where regulations tend to be legal requirements and standards are cooperative requirements. But also in this map are industry alliances, which tend to be more global. Examples that I have listed here, NGMN or GSMA, and then regional or country promotional organizations that are really advocating getting a particular country up to speed in this case, in a lot of 5G environments. But you can see that 3GPP sits here in the standards environment. It is a global example of the standards. And you can also see somewhat more regional basis. But the other thing that does not show up on this slide, that's an animation issue, right where that blue arrow points is the ITU, the International Telecommunications Union, which is actually a global regulatory body. And I say that it's regulatory because the International Telecommunications Union is actually part of the United Nations. And so agreements that the ITU makes are a matter of international treaty. And the 3GPP creates standards that operate not just in the regulatory environments of the different countries, but also in the context of ITU, because the ITU kind of set the framework for what 4G was going to be, and then ultimately also for 5G. And that's the environment in which it behaves. Now, the organization of 3GPP, which is an industry consortium, people from all over the industry are involved, is really built into three pieces. There is the radio access network part, focusing obviously on the radio parts of the network, both the mobiles and the base stations. Then kind of a high-level services and systems area of overall architecture for how services and security, managing interface with the rest of the telecommunications environment are going to operate. And then a third group focused on the core network, and this is the network within a mobile operator that really manages mobility, and that's all mostly done through what we would call a wireline space. But this is different than the network that transports information between cities and that kind of thing. This is the core of the mobile network. But for the sake of today's discussion, we're really focused on the RAN because of the operative word radio and how the 3GPP RAN puts at least their part of the spec together. If you go back to that slide that showed the overview of Release 15, which was just released in June of 2018, that actually covers not just the RAN, but every part of the 5G network in this case. So then this overwhelming slide shows the number of releases that have happened since March of 2000 that have been generated by the 3GPP. And the ones in bold, release 99, release 8, and then what I call release 15A, are the first implementable versions of standards in the case of 3G, 4G, and 5G, respectively. So you can see that it's not just a big bang that says, okay, bam, now we're working in 3G, for instance, in release 99, but there are interim updates or continuing updates. In some cases, these are pretty big changes within a particular generation. So it's not large releases every 10 years as much as it is maybe a generational change every 10 years, but a gradual evolution of capability and then adding to the existing standards. So if we go all the way down to where we are in release 15, in June of 2018, the primary, the rest, I guess, of release 15 was agreed to and launched, specific to some standalone characteristics of 5G. It turns out that release 15 really is not complete. There's a late drop of release 15 that will be agreed upon at the end of this year by 3GPP, and then they've actually already started working on elements of release 16. So you can see this continues on. Now, release 16 theoretically is going to complete the ITU definition of what 5G is, but based on history, you can see that we probably have more coming after release 16 to continue to develop the standard and flesh out all the capabilities that the industry wants. So the other thing that I will cover here is a few different acronyms for people who don't regularly travel in the 3GPP environment. And I won't go through all of these details. You've probably heard some of these, but I'll highlight just a couple. And first of all, the frequency range 1 and frequency range 2, FR1 and FR2. We talk a lot about sub-6 gigahertz for our traditional cellular frequency base, and then we've added what people refer to as millimeter wave above 24 gigahertz. And for now, for the sake of the 3GPP standard, it ranges from 24.5 up to 52 gigahertz. Now, the purists among you all will suggest that 24 gigahertz is not millimeter wave. That doesn't start until you get to 30 gigahertz. But for the sake of the discussion in the industry, the words millimeter wave really mean pretty much anything that goes above 20 gigahertz for the sake of mobile communications. So what's the status of what's happening in 3GPP for FR2, this 24.25 to 52.6 gigahertz? And NR there refers to something called new radio, which is the catch-all term that 3GPP has for the radio interface standard for 5G. So first of all, the 3GPP designates which frequencies they're going to write specifications around and then highlight specific bands. The second thing is the bandwidth of a particular carrier. Most of you probably know that the decisions in 3GPP are to keep everything at the OFDM modulation level, so these are all specified with a certain number of subcarriers. Modulation as simple as BPSK and as complex as QAM, and then a lot of power requirements. Now, I highlight all these tables just to bring to mind a few key things. So first of all, these frequencies that you see in the different band numbers, you can see there's overlap, and this has to do with the fact that while we can all agree on a 5G standard, we really cannot all agree on frequency bands from one country to the next. And you'll note things like the last one, N261, is precisely aligned to the bands that were set up in the United States, which are pretty much characteristic of the U.S., and that territory is a little bit different depending on where you go in the world, but they will write specs around those areas. The next key thing to note are the the bandwidths, the information bandwidth, so the maximum carrier bandwidth that will exist in the standard is 400 megahertz, and most of the work I've seen so far has been with 100 megahertz single carriers with either 60 or 120 kilohertz subcarrier spacings. And but they could go as high as 400 megahertz, and they will be aggregating carriers to get higher data capability. The other thing is the complex modulation that will be used with as much as 256 QAM. That's 2 to the 8th. I highlight that because that means complex modulation and a higher peak to average power ratio with higher demands on things like phase noise and the linearity of your modulators to ensure a decent link. And there's a pretty high demand there on the efficiency and the linearity of the power amplifiers, particularly when you get to relatively high power levels, like in this power class 1 for a UE, that is a mobile device, if you call it. In this case, this is specified around what would be called consumer premises equipment, so it isn't really mobile. It's a terminal that you would mount to the wall of the building to use to receive and transmit on a fixed wireless basis. But you can see effective isotropic radiated power there being spec'd out as high as 55 dBm. So these are not small power levels and fairly high demands given all the other things you see in this table. So given all of that, what are some of the key challenges that we do have in testing FR2 in 5G? And I'm just going to touch on a few of these because the list goes on quite long. So first of all, let's talk about the radiated power from a terminal device. It turns out this comes in 2 different specifications to ensure the device is working properly. Number 1 is the EIRP, and how does this measured? Well, the way that 3GPP has specified this is that we lock the beam. These devices will have phased array antennas in them, and the beam will be electrically steerable, and the test mode that has been provided, in which case the beam will be locked in one position, and then the device will physically be rotated on a spherical grid to search for the highest EIRP. And that peak EIRP, of course, has to be higher than the minimum operational power for that particular power class of device. So pretty straightforward measurement, but devices are not going to work in a beam-locked mode, like that fixed gain horn antenna I had taped to my iPhone. That's just not going to happen. So they're going to be rotating, and this particular illustration doesn't work so well on the animation here, but picture that device constantly rotating. The beam lock is turned off, a viable link is set up with the base station emulator, and the device is rotated on a grid, and the link is then maintained by steering the device antenna such that we get the maximum performance allowed based on how the device is defined. So the beam steering is enabled, you rotate the device on a spherical grid, and the performance is measured on a cumulative distribution function with the EIRP set at a 100% value, the EIRP that was measured in the previous area. And one of the challenges that how are we going to measure these, or how are we going to specify these? Do we specify a single point on that cumulative distribution function or multiple points? And you can also see that some early simulations that were done by, in this case, 5 different companies, you can see at 2 different points on that CDF, 50% and a 20% point, some drastically varying numbers. So as much as 10, 11 dB between different types of devices. And the industry will have to spend some time ensuring that we all have these devices that work on a proper basis, number 1, but number 2, that they're specified appropriately. And originally I thought things were going to be specified on multiple points on that CDF function so we would understand how well the device would work in a optimal situation and how well it would be able to manage its spherical coverage. And here's an example. If you only specify this in one spot, let's say a 50% point, And you could say the requirement is, well, for 50% of the time, the device has to be no less than 10 dB below the EIRP set in the beam lock position. Well, a passing UE could have great performance in one hemisphere and pass this spec, and it could also have zero performance in the other hemisphere. And so potentially that would be a 50% network outage. So if you only specify in one spot, maybe that could be a problem. But it turns out that the way that 3GPP is going to manage this is with a single point on the CDF. But where that point is varies on the power class of the device. And you can see in this table the power classes that are specified on the device and then where the CDF is specified, as much as an 85% rate or down to a 20% rate. And the minimum EIRP based on that area. Now, why would you do this? Well, in the case of that power class 1, it's a CPE. It's bolted to a wall. You're not going to move it around, and so it's a perfect example of the thing I described above, where if you only have decent performance in one hemisphere, that's really all that matters. And so specifying that at an 85 percentile point would probably be fine, whereas with a handheld device, you're going to have to know that at maybe only 20% of the time and less, you would be below that 25 dB EIRP number. So for a device that's quite a bit more mobile and would move around, you'd specify it still at a single point, but at a much different spot on that cumulative distribution function. And the reason why I call this out is that these measurements are difficult to make. You have to move the device around, make many different measurements, and for the sake of making a lot of these devices, it's not very cheap. So let's move on to the next challenge, and this is the idea of making measurements in an area where you need to be confident that you know what's going on. So because of millimeter wave implementation, the ability to make measurements with a cable connected to the device under test is limited, if not just plain zero. So the measurements are going to have to be made over the air, typically inside of chambers of various types. And given that we have a device with a complex modulation and a steerable antenna, the phase of the signal that you're measuring is pretty important. So you want to be in a position where you can make a predictable measurement of both amplitude and phase. And there's this magical limit between the radiated near field and the far field that is 2d squared over lambda. And that is a number that is a great rule of thumb, where d is the minimum diameter that surrounds the entire antenna aperture, and lambda, of course, is the wavelength. And you get an idea that that distance gets farther as d gets larger, and it also gets farther as lambda gets smaller. And we're talking millimeter waves, so lambda is pretty small, and that means the far field actually moves pretty far out. And making far field measurements becomes a little bit more of a challenge. One other thing I'll highlight is the 2 coefficient in front of that D. Some of you who study antennas and make a lot of these measurements already know that that is a rule of thumb. There's a number of things that have to be in place for that 2 to be valid, and it could be larger or smaller depending on what's going on with that antenna. For example, if it's sitting on the top of a car, on the top of a big ground plane, some might suggest that 2 is not the right number. And so there's a lot of education that's going to happen as we move millimeter test into much more of a mainstream environment. So here demonstrates a little bit about this. This is really 3 different tables, the left table being for frequencies 2 gigahertz, the middle one with the red header at 28 gigahertz, and the one on the far right being at 43. And if we just choose a 15 centimeter diameter, about the diameter of, or at least the aspect ratio cross-section of your mobile device that you have in your pocket, you start to see some real interesting issues. And number one is that the far fields start to move pretty far out, 4 meters in the case of 28 gigahertz, and 6.5 meters in the case of 43 gigahertz. And then as you get to larger Ds, like maybe a 30 centimeter diameter where you might be talking about a base station antenna, the far field can move out to 17 meters. That's a pretty big chamber. But what's an even bigger challenge is the path loss at those distances, which will cause some significant problems with dynamic range and measurements. These are a pretty big challenge. There's a lot of ways to overcome these with near field to far field translations, so you can make your measurements closer or do a physical translation with a parabolic reflector, that kind of thing. But you can see the kinds of problems we have with pretty big distances in terms of that near field, far field transition, and also the path losses that make it difficult to make the measurements, especially for low power spectral density measurements. And it gets even more interesting when you talk about the different kinds of devices. There's 3 different categories that are specified, one of which would have, for example, a single antenna in there that would be smaller than the aperture of the overall device. And there's a significant set of arguments around whether the person making the device would make it public how many antennas are inside and how large those antennas are. And hence, you might have to assume that D is the size of the entire device and not the much smaller size of 5 centimeters here. That would work for Category 1, but when you get to Category 2, there may be multiple antennas in the device, and a lot of the designs I've seen so far definitely have multiple antennas in these devices. And in this case, Category 2, they're uncoordinated. So theoretically, you could make measurements on 2 different antennas. And when you get to Category 3, where you have coordinated antennas, then the overall aperture pretty much has to be the size of the entire device. So these become difficult challenges to address. We're doing some really interesting work here. I've seen some pretty innovative stuff going on, both in terms of physics and mathematics, to overcome these challenges. But we're not done, and we still have a lot to learn. So then the last example I'll talk about is measurement uncertainty. As we get to over-the-air measurements, the uncertainties get higher. And the conducted measurement uncertainty for LTE systems, which peak out around 3.5 gigahertz in terms of how they're implemented now. In some cases, I guess they're moving up to 5 for the unlicensed LTE. But the conducted measurement uncertainties are specified by 3GPP as being, they have to be better than plus or minus 0.7 of the dB. And those of us in the test and measurement world consider this to be pretty easy to do. These days, the state of the art is significantly beyond that. And this isn't too hard to manage. But again, if you have a complex system that has to make many measurements, making it consistently that good takes some time and effort, particularly to make it economical. The CTIA has specified radiated measurement uncertainty to be at plus or minus 2.6 dB. And again, this is for LTE. This is the previous generation for frequencies that really don't go over 6 gigahertz. And 2.6 is a little bit of a bigger number. It can be a little bit more intimidating. And so instead of measuring with a micrometer, you're maybe marking with chalk. Well, some of the early estimates for some of the basic measurements, basically power and sensitivity measurements here for devices using either direct far field or indirect far fields like compact antenna test ranges for any delta or any diameter here suggest measurement uncertainties, at least of the initial proposals, and this has been updated, but these are as big as 6.5 dB. And a lot of people will look at this, particularly those experienced in making measurements, and this cutting these things with an axe after you so finely measured with a micrometer is seen to be a little bit absurd. Most of the people that make measurements in anechoic chambers will say they can do a lot better than this. And definitely we as an industry will gravitate to numbers that are a lot better. But the initial estimates were pretty bad, and that's because you have to add up a number of issues, not just the test equipment, but the interconnections, up conversion, down conversion, errors in the chamber, quality of quiet zone and ripple in the quiet zone and that sort of thing. And these do add up, and it's going to be harder to make these measurements. And, of course, getting these measurements accurate turns out to be a pretty important thing to do in order to not just guarantee the performance of the system, but the how you're going to manage regulatory limits. And here's an example, and again, I use this in a live audience. This was created by my colleague Maureen Rumney. Consider a microwave oven. The top-end microwave ovens have a total radiated power of about 700 watts at 2.4 gigahertz. And let's open up the door. I know, of course, these ovens will turn off when you do that, but let's say they didn't, and you have a 700-watt microwave oven radiating with an open door. I wouldn't feel too good about walking out in front of this oven. Well, what's the difference between that and 55 dBm from a CPE specified by 3GPP? 55 dBm EIRP is well within the limits of what the FCC would dictate. Now, this isn't really fair because EIRP is different than TRP, but when you're standing right in front of that oven and standing right in front of this CPE, maybe it may not seem that different because you're in the hot seat. So those of you who know how to do the mathematics, and I think all of you do, what is the difference between these? And the answer is about 3.5 dB. So 700 watts is about 58.5 dBm, something like that. So if your measurement uncertainty is over 3.5 dB, you can see the differences from a practical sense you're going to get into. Now, I made the mistake of putting this slide in front of an audience that immediately got into an argument about the relative health effects of this kind of radiation, non-ionizing radiation. And my intent is not to bring up that topic. But my intent is to ensure that we all think about making accurate measurements so you know where you are for the sake of performance and also to fit within the regulatory limits. I will leave the health effects arguments for a different audience. But it is important that we measure these things, and this is how I really like to finish my slides. It's what I do for a living. I've worked in the test and measurement industry for my entire career since 1985, and we started out early in my career with quotes from this gentleman, William Thomson, and I think most of you are aware of this, is that you've got to be able to measure this and speak about it in numbers, and you know something about it. But if you can't, your knowledge is of a meager and unsatisfactory kind. And so our intent is to continue to improve how these measurements are made, make it easier to make them more accurate, and work with the industry to make sure that happens. And it's been a lot of fun to do that. And it's very interesting to see the commercial communications industry adopt a set of technologies that have previously really been the domain of aerospace and defense and much more obscure areas. So we will get to everyday millimeter wave, but it's going to take some time. And the industry is working through a number of these challenges, and it's really up to us radio experts to help them address all of those. And it's not just the physics, but also all of the digital capabilities and the ideas of making sure it behaves the way that you designed it. So with that, I will open this up to questions, and I think those will be moderated by the team, and I will stand by and get Mike and Ramesh to help with that process.
Excellent. Thanks a lot, Roger. I think you did a really fantastic job of presenting something that looks like it's got some really significant challenges ahead for everybody on the measurement side. So you're right, it is time for the question and answer session. We just have a couple of questions right now, so there's plenty of time and space available for other questions. Just remember to submit those to the Q&A panel there in the audience window. Okay, so we can start going through some of these, and I'll try to not let any of the health-related ones sneak through. So I think you covered the EIRP numbers, but there's also a question about, do you see gallium nitride PAs in mobile handsets?
So this is a really good question. I was involved in a heated discussion at the GSMM back in May about whether or not we would get 3.5 technology or compound semiconductor technology for the sake of millimeter wave in handsets. And I think everybody knows that every handset that's made now, the smartphones typically have gallium arsenide front ends. And so will we continue to move more exotic materials into the handsets? And my personal opinion, and I hope people prove me wrong on this one, but my personal opinion is that it's unavoidable. I believe that the demand that the system will have on the efficiency of the power amplifiers and the requirements for maintaining a decent link will be such that it's going to be very difficult to do this without compound semiconductors in both the base station and in the handsets. And the question is, can we do gallium nitride? And one of the issues with gallium nitride is that while it is quite a bit more efficient than silicon, certainly, and even gallium arsenide at high power levels, at lower power levels, it turns out it isn't very efficient. It's a bit of a problem. And the systems are managed to operate these handsets at the lowest possible power level they can, mostly to save power and to manage interference. And so I think if we do get to gallium nitride in handsets, there's going to have to be, I know there's a lot of research on this now, but there will have to be advancements made to improve the efficiency and the performance of gallium nitride at relatively low power levels because of the range over which these handsets are going to have to operate. I know that gallium nitride made a big entrance in terms of LTE base stations, and so the cost of gallium nitride front ends has come down quite a bit because the volume has forced a lot of advancements in manufacturing technology and simply economy of scale. But it remains to be seen how well it will work in a handset environment, but I tend to think that we're going to need even more compound semiconductors. And silicon at 28 gigahertz is probably operating just barely above 10% in terms of power amplifier efficiency, and it's pretty tough to maintain battery life and heat management in devices with such low efficiency.
Okay, yeah, I think that's totally fair. Thank you. So we'll jump around a little bit here. Here's a comment about a table that you showed for the different power classes, and specifically which FR2 band is that for? Or stated another way, is it the same for all of the FR2 bands that you showed?
So I'll put the table up here again. Hopefully this comes through. Let me know, Mike, if it does.
Yeah, that's what they were talking about. Yep.
Yeah, so this table, and this will be out there for a reference, and you can even get this from the 38.101.2 from 3GPP. This is all in the public domain. But you can see how the different power classes, and I just put power class 3 and power class 1 in this table. There's a more advanced table with more information in here. You can see that for the different bands, they're a little bit different, and this clearly has to do with the frequency, right? So everything that's below 29 gigahertz is at a certain power level, and then they back off of that a little bit for the N260, which is up to 40 gigahertz. You can expect this to continue to evolve, and that's because the U.S. just allocated up to 47 gigahertz, and there are other countries that are considering things as high as 52.6. 3GPP hasn't specified anything up there yet, mostly because they don't have to. They got their hands full working through all these other things, but that's coming, and I expect that a full table that would represent all the power classes, and then ultimately all the bands that get allocated, these are the only ones they've specified so far, will have a little bit more of a complex picture that you can see for anything other than a CPE. They're going to allow these power levels to be a little bit lower for the higher frequencies. It's just that much harder to get up there. I hope I answered that question.
I believe so, yeah. And this is great. We've got a lot of questions rolling in now, so thank you to the audience. We'll try to get to as many of these as we can. Let's see. What are the different pieces of equipment that you would need to do the kind of tests that you're talking about here, and any kind of rough order of magnitude cost estimates?
That's an interesting question and a little bit difficult to go through all the details, but the fundamentals, and I'll click on this slide to indicate a couple things. If we're just talking about measuring user equipment, the device that is either a CPE or a handheld, it depends on what measurements you're going to make. If you're going to make measurements on the components therein, like front-end modules and power amplifiers and that kind of thing, you typically need some sort of generation of a complex baseband, a translation up to millimeter wave frequencies to the right power levels, and then some means of measuring a measuring receiver. And so that's kind of fundamental. You don't need to have an active link running. But once you get a device that's assembled and working, in this particular example, the test equipment actually would be a base station emulator, a network emulator that would be able to maintain a link with the mobile and maintain an active link with the mobile and actually make the measurements on the power levels and, for instance, many other things. Not only that, this particular setup would require a chamber, anechoic chamber with a positioner that would move the device around, and all of the associated probe antennas and cables and actuators and so forth to make those measurements. And all of which would have to be done with an active baseband processor for maintaining the link, and clearly the RF pieces and the millimeter wave pieces that would maintain, the right power levels on an active basis and steer the antennas around and so forth. So 4 millimeter, and then the other angle in this is just basic S parameter network measurements. If you go back to much more simple devices, it looks like that. And then the other territory that a lot of work happens in is making measurements on the base stations themselves. And once again, it starts with making measurements on the components, the front-end modules, that kind of thing, which you can do with S parameter measurement capability or basic source analyzer capabilities. And then once we get into making active measurements, some sort of a UE emulator that would do an end-to-end test of how well that base station equipment would work. Is done. So it's kind of a wide answer of the different kinds of tests you'd have to do. It depends on what your technical challenge is. The characteristic, though, of the millimeter wave space is that it is expensive compared to the sub-6 gigahertz area. And this is because, as we talked about before, the semiconductors involved are more exotic and more expensive. The mechanical tolerances of the packaging and all the other things you have to do to get this right are much more precise and expensive to manage the mechanical tolerances of everything that you're putting these things in. And then you have chambers and positioners and expensive software to move things around. And so it does become more expensive. And this is probably the biggest challenge we have from a test and measurement standpoint is how do we, if you're going to make this really everyday millimeter wave, how do we move from a place where, maybe a couple of thousand engineers around the world, I don't know if that's the right number, but it's not huge. We're doing a lot of measurements on millimeter wave, and we're going to move to tens, if not well over 100,000 engineers that are going to need these tools. And we're going to have to scale that, and the price of this stuff is going to have to be managed such a way that it does scale. And it's also relatively easy to use. People are going to have to move from very obscure, difficult measurements made in chambers to things that look a lot more like push button. So that's a big challenge, and the prices range all over the place. But one thing that we're working on very hard in the industry, my company and those, my competitors as well, is to make this stuff more affordable as the audience that makes these measurements expand.
That's great. I think that was a really, really complete answer. Thank you for that. Let's get to a couple other ones here. This one is really specific, but it seems relevant, so I'll ask it and see what you have to say. So when do you think 3GPP will publish 38.141 for measurement methods for REL 15 for FR2? It's really specific, but it involves measurement method specifications. So
yes, it does. Yeah, so I manage the team, at least virtually, that works on 3GPP with this work. And there's a lot of pressure to get that done at the next meeting, which is a mix of what's happening at RAN 4 and RAN 5 in early October. I hesitate to speculate on this because the original plan was to get this stuff all figured out probably by the springtime in 2019, and there is a lot of push to accelerate this work. And so I can't guarantee timing on this because 3GPP is, while they can say we will publish by such and such a date, in a lot of cases these specs get published and there's a long list of exceptions. Release 15 is a perfect example of that right now. And so the measurement methods are probably going to be complete, I would say, by the end of this year. But there's a number of issues that still have to get worked out. One of the big ones that we're working on right now is measurement uncertainties, as I stated. But it's coming, and some of this stuff is already figured out, but there's a lot of things that still are not. There's some TBDs in those documents.
Okay, great. Sorry, I guess after I read it, I think maybe I threw you a live hand grenade. Sorry about that.
It's okay.
Okay, well, let's go with a slightly easier with it. Do you think 5G adoption will be everywhere, along highways or just in data-intensive urban centers? And then a follow-on comment there is the number of base stations required seems daunting.
Yeah, this is a very good question for allowing me to capture a couple of key points. So first of all, 5G is not just millimeter wave. 5G is a new standard for operating from bands from 400 megahertz up to 100 gigahertz. So will it be everywhere? Well, ultimately, it will be as prevalent or ubiquitous as 3G or 4G, I believe. Now, whether or not that's all millimeter wave remains to be seen, because in the millimeter wave space, my guess is that because of the unique challenges this has, it will be used where it will generate the most revenue. And typically that's in urban environments where you're going to see relatively heavy data use, or maybe even private networks that use the 3GPP standard where heavy data use is required, and it can be constrained to an area which is easy to manage. And the number of base stations is daunting. And that's not just for millimeter wave, but also in general, the best way to get spectral efficiency is to decrease the cell size, because it's all about bits per second, per hertz, per square meter. And there is a lot of work going on from a policy standpoint to allow a higher density of base stations to be placed without going through what amounts to a very painful set of legal processes, municipality or neighborhood by neighborhood, but also make sure that we manage, the regulatory limits and everything like that. It is a very tough thing to manage. So I think the industry still has a lot of work they have to do there, managing backhaul and all those other kinds of things. But, everywhere is probably an exaggeration. I don't think in my hometown of Simla, Colorado, of 500 people, there's going to be a lot of 5G for a while. But I do think that it will be as prevalent as you see earlier generations, but it won't happen overnight. It will take time, and millimeter wave will probably be more constrained. And it will roll out in phases. Different countries are moving at different speeds.
Provides a lot of growth for the future, but slow.
Absolutely.
Yeah. Well, that's great. Thank you very much, Roger, for answering those questions. And there are still a lot of questions here in the queue, and I believe we'll be able to get the presenter to answer those offline. As we said earlier, this session will be archived on the Society website at mtt.org, and all the registrants will get an email reminder with a website address when that is available. For the attendees who would like to receive PDH credits, please follow the link in the webcast view and also use the code provided on the last slide of this presentation, which is shown right now. There's a code there that you can use. Once again, I'd also like to thank Mr. Nichols for this excellent and informative presentation. Special thanks to our audience today for joining us. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thanks, and have a great day.